Hi everyone, I'm Mikhail. Welcome to the Dark Wire Labs YouTube channel where we break down network technologies and bring them to life with real code. In today's video, we are exploring EVPN, what it is, where it's used, and why it has become so popular in modern networks. As always, at the end of the video, we will build a hands-on demonstration where Linux containers form a simplified data center fabric using EVPN as the control plane. Let's get started. EVPN stands for Ethernet VPN. It's a standards-based control plane that provides Ethernet multi-point connectivity over an IP or MPLS network. Traditionally, Ethernet networks learned where devices were by flooding traffic, sending frames everywhere until the correct device responded. EVPN changes this model completely. Instead of relying on data plane flooding and learning, it uses multi-protocol BGP as a control plane to proactively distribute reachability information. In simple terms, rather than learning by trial and error, switches, also known as VTEPs in VXLAN networks, advertise MAC and IP reachability information to each other in advance. You can think of it like a GPS system. Instead of driving randomly and hoping to find a destination, every participant already knows the best path. EVPN has become the Swiss Army knife of modern networking. It is most commonly used in data center fabrics, typically paired with VXLAN to build scalable leaf and spine architectures. It's also widely used in data center interconnect environments, where multiple geographically separated data centers are connected and operate as a single logical network. Service providers use EVPN to replace older technologies such as VPLS, gaining better scalability and control. Even enterprise campus networks can leverage EVPN for macro segmentation, creating large-scale security zones across buildings or campuses. Key advantages of EVPN: reduced flooding. It minimizes BUM, means broadcast, unicast, and multicast traffic by using BGP to distribute MAC addresses. Multi-homing allows a server to be connected to two different switches simultaneously for redundancy, active-active, without creating loop. Optimal routing supports Anycast gateway, which means the default gateway is present on every switch. This prevents hairpinning where traffic is going back and forth unnecessarily. Protocol agnostic. While often paired with VXLAN, it can also run over MPLS or SR version 4. To understand the VPN, you must separate the network into layers. The underlay, the physical hardware and routing, OSPF, ISIS or BGP, that ensures all switches can talk to each other's physical IP addresses. And the overlay, the virtual tunnel, that carries the actual user data between VMs or containers, making them feel like they are on the same wire. In this architecture, EVPN is the control plane and VXLAN is the data plane. EVPN uses specific BGP route types to communicate different kinds of information. Type 1 is Ethernet auto-discovery. It's used for multi-homing and telling the network a device has moved. Type 2 is MAC IP advertisement. It tells the network MAC address A and IP B are located behind me. Type 3, inclusive multicast. It's used to set up the path for broadcast multicast traffic. Type 4, Ethernet segment, used to discover other switches connected to the same multi-home device. Type 5, IP prefix route, used for routing between different subnets layer 3, rather than just bridging. In real-world deployments, Type 2 and Type 5 routes are the most commonly used. In today's demo, we will review VPN Type 2 routes exchanged between two Linux containers, simulating a simplified data center fabric. Both containers will run MP-BGP to exchange VPN Type 2 routes in order to learn each other's MAC and IP addresses. They will also act as VTAPs, means VXLAN tunnel endpoints, to form the VXLAN overlay network. This setup simulates a simplified span and leaf data center topology where we only have two leaf switches directly paired with each other. On each node we create a Linux bridge, a VXLAN interface, VXLAN 100, VNI 100, and a tenant network namespace, representing a tenant host connected to the leaf. In the first part of the demo, we will use FRR service in Linux to implement EVPN using a production-grade control plane. Its commands are very similar to Cisco OS, and that's good for our demonstration. In the second part, we replace FRR with our own simplified MP-BGP EVPN implementation, written in Go language. It establishes a TCP session on port 179, exchanges EVPN Type 2 routes, and programs the Linux forwarding database to install learned MAC entries and associated remote VTAP next hops. As a result, tenant hosts can communicate over the VXLAN overlay and can successfully ping between overlay IP addresses. Let's get started. So this is my lab, where I created two instances of Linux container running FRR routing service in Linux. I created here VXLAN interfaces, and actually the main purpose why I wanted to use FRR was to just try establishing BGP peering, MP-BGP, in order to exchange EVPN route type 2 information between these two containers, just to confirm it's working. And the next step is to implement the same BGP process, but to write an own program in Go language. So that's the first part. Let's just open one of the containers. I'll connect to FRR. That's one of the routers. I just change host name to make it one. So here I configured BGP for the address family EVPN. As you can see, the BGP session is established with my neighbor, which is in the other container. Now let's check what EVPN routes we advertise and learn. So we are interested to see type 2 routes for IP and MAC address, and here they are. Okay, so actually these two are the routes we are announcing, because that's actually for our overlay IP address, and that's our IP, and this is our neighbor. So we see two records. This one we can ignore, it's for IPv6 address, we are not going to use it. But this one is actually, it's EVPN type 2 root record containing the MAC address and IP address of the opposite side, which is in the other container, and that we learned through MP-BGP. Okay, good. So that's the control plane. This is how our host will learn the MAC address and IP mapping of the remote end, and also it learns next hop. Using this information, we will program the forwarding database of our Linux kernel to be able to speak to the other side of the overlay. Okay, but that's just to test operation of BGP. The main purpose is now to implement this in the Go language, our own BGP implementation. Before I proceed to the part 2 of our lab, let's quickly take a look at the packet capture of the BGP message exchange between our routers. So I captured traffic while the routers were sending updates, and here I just want to show you how it looks like. So here inside BGP protocol, we see that there is pass attribute for an RI, and here we have inside we have EVPN type 2 root, because here that's the root type, it's MAC advertisement root type 2, where actually specify the MAC address and IP address mapping and VNI that will be mapped to VXLAN 100. Okay, and that's the second one what we saw for IPv6, but we are not going to use it. Okay, and now let's proceed to the second part of the lab. That's my project for part 2 of the lab. So I still use Docker Compose. Actually, I just modified the previous project because I wanted to also include my own program written in Go language. Here it is. I will not go in detail through the code because it's pretty long. I spent a while speaking with ChatGPT to make it generating the right code for me, what I actually need. And the requirement was I needed implementation, working implementation of MP-BGP with EVPN to establish TCP connection with the peer, to exchange EVPN type 2 routes, to parse it, and finally to program our forwarding database in Linux to install these routes there. Yeah, and this code actually it supports only type 2 routes, nothing else. Yeah, but that's sufficient for our demonstration. So this project, it creates just 2 instances of a Linux container. They're similar, and I use a shell script to prepare them for the demonstration. So by default, each container has just one network adapter, Ethernet 0, and in this script, what we do, we also create bridge interface 100. Then we create VXLAN interface for VXLAN ID for the VNI 100. And actually we take variables from a separate file from config.inf. So for each container we get the node name, the peer IP address to connect to BGP port, that's default one, autonomous system number, peer's autonomous system number, VNI, yeah, and whether this node should initiate connection or should listen to connection from a peer. Okay, so that's a VXLAN interface for the overlay, right, for the data plane that we will establish using our control plane that our program will represent. And we create a tenant namespace which will also represent overlay, assigning IP address here, and finally we will test it by pinging one node from the other node through the overlay network. Okay, and just one more clarification for this record, why we need it, because that's a very simple demonstration, so we use just flooding approach here. So once we don't know MAC address, we will just flood it, this broadcast traffic to the neighbor through the VXLAN interface. However, it will be overwritten by the BGP control plane once this EVPN root type is received and installed. And that's name of our program. So let me run it. Okay, both nodes started successfully. Yeah, I can see it here. Now let's go through the logs, because logs are very important here. So since the code of this BGP implementation was really long, I had to set up the detailed logging so I can monitor each and every step here. So let's see what's going on here. So for example, node 2, it took the configuration, it identified the peer IP address, ASN number, and so on. Then it started listening, because the mode was to listen, not to initiate connection. Then it received connection from the neighbor, that's node 1 IP address, and also from node 1 log we see that it here it connected. So then they send BGP open message, BGP established, and the most important is update message, where the EVPN type 2 messages are being exchanged in both directions. So it's node 2 who sent it, and also node 1 who sent it. And what they're actually sending, they're just sending the IP and MAC address of our tenant virtual interface that we created in each node to test the overlay network. Yeah, and so here we see detected, type is correct, and then it's, yeah, that's the next hop learned. And the last step is to program the forwarding database with this information. Okay, so logs look good. Now let's connect to the containers and perform some basic tests. Okay, that's node 1. Yeah, underlay. We call it underlay because that's this interface is used for communication between the nodes. So that's IP address .2, and the other node IP address is .3. So what we will test here, we tested the underlay now. We see from the logs that BGP session was established. We can actually also check it here through net start. Yeah, you see there is an active TCP connection on port 179 initiated by node 1 to node 2. Good. And yeah, it's sending keep alives to keep the connection active. What else? Let's check the VXLAN interface which we created. Link show VXLAN 100. Okay. And we see this interface is up. Let's check the forwarding database. It's breach FTB show. Let's check breach 100. Means what's learned from this breach. Yeah, that's our record which was injected in the forwarding database by our BGP program, the BGP process, because it was learned from the peer. And the other peer, it should also have the same one. Breach show. Yeah, and this one has 4.3. Okay, good. What we'll do now? Now we want to ping it. But before we ping it, let's check the overlay network configuration. Since we created a tenant namespace, tenant, okay. That's the IP address, that's node 2, and here it's should be .1. Yeah, that's a node 1. So that's it. This will represent the overlay network. And finally, what we need to do, we need to ping one from the other one. I will run TCP dump here. I will run it. Okay, I will not specify interface. Now from here I need to ping the other end from the overlay, from the tenant namespace. We will send 2 packets, 2 SMP packets. Okay, 2. Some traffic. What's that? Okay, that's BGP keep alive. I'm stopping the packet capture, and now let's see what we've got. So I was capturing it on node 1. I didn't specify the interface. Let's see. Here we receive this ICMP echo packet. Actually, yeah, that's the echo reply, if I'm not mistaken. Yeah. From 1 to 2. Wait. We were pinging 2. Okay, yeah. Sorry. It came from 1 to 2. It's echo request, of course. Even the type is echo request. So this packet is captured from the overlay. So that's why we just see it as ICMP. But also at the same time we captured packet from the underlay. And in the underlay it's recognized as VXLAN with VNI 100. And it's sent from this IP to this IP. These are underlay IP addresses. Actually, it should use UDP. Then we have echo reply. This is BGP, we skip it. And again, it's encapsulated in VXLAN. So it will be UDP, source port, destination port for VNI 100. Yeah. So that's how it looks like. And I'm really glad this lab is working as expected. And just to recap, so what we did, we built our own control plane through multi-protocol BGP to implement EVPN and exchange route type 2 advertisements for MAC addresses and IPs. And then we also configured the data plane by creating VXLAN interfaces and the tenant namespaces. That's what our script did. This and this. And the fact, once we received this EVPN type 2 routes, we injected them in the forwarding database in Linux kernel, and this helped our data plane to forward packets and to deliver ICMP packets between the nodes. I hope you like this demonstration. See you in next video. Bye.